Today we are going to discuss about the registers. Register is a group of flip-flops which is used to store the data. So we already seen that for a flip-flop it is able to store one bit of data. So if you have n flip-flops, so we can store n bit of data. So these registers we use to store the data. Now, after this registers, we are going to discuss about the counters. The main difference between this register and counter is that for a counter, there is a specific sequence of states, but in registers, there is no specific states except in some certain specialized applications. Now, there are different types of registers are there. Registers which is used to store the data, which is known as the memory registers. Then another type of register is the shift register. Now, this shift register, it is able to shift the data from one location to another location. So there are two types of shifting possible, that is either to the left or to the right. So this type of operation is possible in shift registers. So it permits the data storage as well as the shifting of data from one location to another location. Now, based on how the shifting is taking place and how the data is fed in and how the data is taken out, based on that, these shift registers are classified as serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. So as the name indicates, serial in, serial out means the data is fed serially and the data is taken outside serially. Then serial in, parallel out means the data is fed serially but the data is taken parallelly. Now serial in, serial out means the data is fed parallelly. That means the same at the same time all the data is available for all flip-flops. Then that data is taken out serially. Then the last one is parallel in, parallel out, where the data is fed parallelly and the data is taken out parallelly. First, we can discuss serial in, serial out shift registers. In the slide, of orbit serial in, serial out shift register using JK flip-flop is shown. So the data is fed to the J terminal of the first flip-flop. Then the data is taken out from the terminal Q of the fourth flip-flop. Now suppose if you want to transfer the data to be transferred is 1 0 1 1. We know that for a JK flip-flop, if J is 0, J is 1, K is 0, the output, next stage output will be 1. Then J is 0, K is 1, then the next stage output will be 0. So this is the combination that is possible here, because here you can see that for each and every flip-flop we are feeding J terminal and K terminal as the complementary. So first you can see that we are feeding the data directly to the J terminal and its complementary is fed to the K terminal. Similarly, the second flip-flop J is fed from the Q output of the first flip-flop and K terminal is fed from the Q bar output. So each and every flip-flops the input is complementary. So these two combinations is possible. That is when J is 1, K is 0. When J is 0, K is 1. Now for the data to be transferred is 1 0 1 1. So the first data to be entered is this 1. So this 1 is given as the input of the first flip-flop. This J terminal is given as 1. So the K terminal, it will be 0. And initially we are supposed, if we are assuming all the flip-flops are reset, so this input will be 0, this will be 1, this will be 0, and this will be 1, this will be 0, and this will be 1. So the final output, that is also will be 0 and 1. Now this is a stage when you apply the first clock pulse. Here you can see that the clock pulse is applied to all the flip-flops at the same time. That means all the flip-flop will change their output at the same time. So when you give the first clock pulse, you can see that the first flip-flop input is 1 0 and all other flip-flop input is 0 1. So when the clock pulse comes, the output of the first flip-flop will be 1 0. Then the second flip-flop will be 0 1. Third will be 0 1, and the fourth will be 0 1, because when the clock pulse comes, the input is 0 1. Now this is the stage, that is the first clock pulse output. Now when the next clock pulse comes, we have to transfer the next data to be transferred is again 1. So what you will give? You will give 1 to the J terminal, so 0 will be appear at the K terminal. At that time, the input here, when the first clock pulse comes, the output of the first flip-flop is 1 0. So that will be fed as the input of your second flip-flop. So the input of the second flip-flop is 1 0. So the output will be again 1 0. Then the input of third flip-flop is 0 1, so the output also will be 0 1, and the next that is fourth flip-flop output will also be 0 1. So when you check, you can see that the output of the first, that is QA, is just jumped to QB, and the output of QB is jumped to QZ, and the output of QZ gets jumped to QD. Now when the next clock pulse comes, that is we have to transfer the data as 0. You will make your J terminal as 0 and K terminal is 1. So the output of the first flip-flop will become 0 1, and here initially when the third pulse comes, the input of JK flip-flop 2 is 1 0, so the output will be 1 0. And when the second clock pulse is applied, the output of the second flip-flop is also becoming 1 0. So the input of third flip-flop is 1 0 when the third pulse comes. So the output will again become 1 0. Then the input of fourth flip-flop is 0 1, so it will be 0 1. So in the next stage, you can see that this output of each flip-flop is jumped up 1 bit. The same is the case with the fourth clock also. So in the table, it is clearly shown. So here you can see that initially all the flip-flop output is 0. That is, we are resetting all the flip-flops. So if the first data to be fed is 1. So when the data 1 is fed to the first flip-flop, and when you apply the first clock pulse, the output of QA become 1. All other output is 0. In the next clock pulse comes, this 1 get shift to the second flip-flop, and the second input is again 1. We have to transfer 1 1 0 1. So the second input is also 1. And when the next clock pulse comes, the output of QB, that is second flip-flop, is jumping to the QZ, and QA is jumping to the QB. Okay. Now similarly, this thing, that means when you apply the clock pulse, the bit, that is the input data, get shifted by 1 bit. So at the output, when the fourth clock pulse comes, at the output it will be 1. When fifth clock pulse comes, the output will be again 1. When the sixth clock pulse comes, output will be 0, and when the seventh clock pulse comes, the output will be 1. So this is how the serially the data is fed in, and data is fed out. So in the slide, the timing diagram for the serial in serial out shift register is shown. So here it is marked as A, B, C, D on the top. That is, and this is a clock signal applied. This is the data we applied. This is the QA, QB, QC, and QD. Now when the first clock pulse comes, you can see that we have to transfer the data as 1 0 1 1. That means the first data is 1, second data is 1, the third data is 0, then fourth data is 1. So first data to be transferred is 1, so we will make the JK flip-flop output serial input as 1, J as 1, and K as 0 when the first flip-flop comes. So the output of QA will become 1 at that time, and all other flip-flop output will be 0. Now when the second clock pulse comes, we have to transfer the next data to be transferred is 1. So we will make a JK input as this as 1 and this as 0. So the output of QA will become 1. So the input of QB is actually, that is the input of second flip-flop is actually QA and QA bar. So QA is fed to the J flip-flop and QA bar is fed to the K terminal. Now this here it is 1. The data before applying the clock pulse is 1. So that is the output of QB will become 1. Then when the next clock pulse comes, we have to transfer the data as 0. So we will make 0 as the input JK. Now for the flip-flop QB, that is the second flip-flop, the data is 1. That is before coming the third pulse, the data is 1. So the output will become 1. Then for the QZ, that is the data is 1. Before the clock pulse comes, the input data is 1 0. So the output will become 1. Now if you take QD, the input is 0, so the output will be 0. So this is the timing diagram for a 4-bit serial input shift register. The serial in serial output shift register that we discussed is using JK flip-flop. Now using D flip-flop also we can have the same 4-bit shift register. So in the slide, the diagram for the serial in serial out shift register using D flip-flop is shown. Here also 4 flip-flops are there: flip-flop A, flip-flop B, C, and D. Now the data is fed here and the data is taken out here. Now the data to be transferred that we will apply here in the first flip-flop input. Second flip-flop input is the output of the first flip-flop. Then third flip-flop input is the output of the second flip-flop. So the same is the case with here also. That is, if you want to transfer 1 0 1 1, we will feed a 1 as the input to the first flip-flop. Now when the first clock pulse comes, this will become 1. Here it is 0, so that will be shifted 1 bit. So when the each clock pulse comes, it is getting shifted by 1 bit. The other cases is similar to that of JK flip-flop. Now the registers that we discussed is shift right register, that is data is shifting to the right side. Now the shift left register you can obtain using the rearrangement of the flip-flops as shown in the slide. Next is serial in parallel out. So circuit of serial in parallel out shift register is shown in the figure. So as the name indicates, the data is fed serially and the data is taken out parallelly. That means we will be taking the output at the same time from all the flip-flops. So here again 4-bit shift register is shown. Now the data is fed serially to the first flip-flop and the data is taken parallelly at the same time from all the flip-flops. So suppose if you want to transfer the data as 1 0 1 1, again the same, and you can take. And now here you can see that initially we will make all the output of your flip-flop as 0 by using the clear pin. So all the output will be 0 initially. Now when the clock pulse is applied, when the first clock pulse is applied, you have to ensure that the data to be transferred is applied to the first flip-flop. So the data to be transferred to the first flip-flop, it is 0. So we will apply here, sorry, it is 1. So we will apply here 1. When the first flip-flop comes, so you can see that the input of the first flip-flop is 1. All other flip-flop it is 0. So when the clock pulse comes, we know that for a D flip-flop, the data output will be based on the data input. That is, if it is 1, the output will be 1. If it is 0, the output will be 0. So the first flip-flop output will become 1. Then second flip-flop output will be 0. Third flip-flop output will be 0. And the fourth flip-flop output will be 0. Next, the next data to be transferred is again 1. So we will make the first flip-flop input as 1. Now when the clock pulse, second clock pulse is applied, you can see that for the first flip-flop the input is 1, for the second flip-flop is also input is 1, for third it is 0, then fourth it is 0. So when the next clock pulse comes, the output of the first flip-flop will become 1, second flip-flop is again 1, third flip-flop it will be 0, and fourth flip-flop it will be 0. Okay, now for the next, before applying the next clock pulse, we will be applying the next data to be transferred, that is 0. So we will make this as 0. Now when the next clock pulse comes, the input of first flip-flop is 0, so the output will be 0. The input of second flip-flop is 1, so the output will be 1. Then the input of third flip-flop is 1, so the output will be 1. And the fourth flip-flop it is 0, so it will be 0. Now we will apply the next bit that you have to transfer, that is 1. So the next data that we will apply here 1, and when the clock pulse apply, the first flip-flop output will be 1, the second flip-flop output will be 0, third flip-flop output will be 1, and fourth flip-flop output will be 1. Now all the 4 bit we transferred. Now we will take this data serially as the out. So at the output we will get the data as 1 0 1 1. Timing diagram for the register is shown in the figure. So we were making initially all the flip-flop output is 0, and when the next clock pulse comes, so we are ensuring the data is 1. So when the data input is given as 1, so the first flip-flop output will become 1. Then second flip-flop output it will be 0. The third it is 0, and the fourth it is 0. Because for the second flip-flop the input is QA. Then for the QC, that is the output QC is based on the output QB, that is previous stage QB. Now when the second clock pulse comes, you can see that we are applying a data bit as 0. So the first flip-flop output will be 0. Now if you take the second flip-flop, what is the data available at the QA in the previous stage, that will be appear as the input of QB. So you can see that it is 1, that is before applying the second plus, the input is 1. So the output will be 1, all other output will be 0. Now when the next pulse comes also, you are applying a input data as 0, so the first flip-flop output will be 0. Now before applying the third pulse, the output QA is 0, so your QB will also be 0. Now before applying the third pulse, the output QB is 1, so your QC will be 1, and QC is 0, so the QD will be 0. So this process continues. In the slide, a parallel in serial out shift register is shown. So here you can see that, as the name indicates, the data is fed parallelly and the data is taken out serially. So here you can see the arrangement. Here also we are using 4 flip-flops, so 1, 2, 3, and 4. So the input data we have to apply parallelly, and we have to take the data as serially. So input data is fed parallelly means all the flip-flop will be fed using the external data at the same time, and we will take that data as serially at the output. So here you can see that we are using one additional control here, shift bar load complement. That means when this one is when this pin is 1, we will get a shift operation, and when it is 0, we will get a load operation. So if you first we want to load the data, so we will make it a 0. When we are making this as 0, you can see that this line will be 1. So this line will be 1 and this line will be 0. So you can see that this will be 0, this will be 0 and this will be 0, and here it will be 1, this will be 1 and this will be 1. That means one of the AND gate, that is G4, one of the input is 0, G5 one of the input is 0 and G6 one of the input is 0. That means for that AND gate the output is 0. So this will be 0 and this will be 0 and this will be 0. Now the second AND gate, that is connected to each OR gate. So G1, one of the input is 1, the second input is D1, so the output will be D1. Similarly for G2 it will be D2 and for G3 it will be D3. Now if you take the first OR gate output, you can see that 0 plus D1, so this will be D1. Then for second OR gate it will be D2 and for third OR gate it will be D3. And for the first flip-flop it is D0. So now you can see that when shift load pin is made 0, all flip-flop will be driven by the data input. All the flip-flop, you can see that the first flip-flop the data will be fed as D0. Then for the second flip-flop the data available is D1, for the third flip-flop it is D2 and for the fourth flip-flop it is D3. Now when you apply the clock pulse, what happens is that all the flip-flop output will be changed according to the data input D0, D1, D2 and D3. So the output Q0 will be becoming D0 when the next clock pulse comes, and Q1 will become D1, Q2 will become D2, Q3 will become D3. Okay, so that is the loading operation. That means we are loading each flip-flop using the data that we have to shift. Now next we have to obtain the shift operation. To get shift operation, we have to make this shift bar load complement pin as 1. So when this is made as 1, this will be 1 and this will be 0. Now you can see that G4 the input is 1, G1 it is 0, and for G5 it is 1, this will be 0, this will be 1 and this will be 0. That means the G4 output will be, that is whatever be available at Q0, and the G5 it will be Q1 and G6 it will be Q2, and we have a final output Q3. Now this will be 0, this will be 0 and this will be 0. That means the output of G1, G2, G3 will be 0. Now if you take the output of the first OR gate, it will be Q0 and the second output will be Q1 and third OR gate output will be Q2. That means the data that is available at the output of the first flip-flop will be available at the input of the second flip-flop. Similarly for the third flip-flop the input is the output of second flip-flop, and same the case. That means when you apply the clock pulse, what happens is that the data that is available at the first flip-flop will act as the input of the second flip-flop. So this is the case of a shift register. Now when you apply the clock pulse, this output will get shifted. That means whatever be the available here, that gets shifted to here, then here to here and here to here. That means we will get a shifting operation there. So this is the parallel in serial out. The data is fed parallelly and the data is taken out serially. A logic symbol is shown at the bottom of your slides. And the figure it is shown the timing diagram. So here you can see that we are applying clock pulse here. This is the shift load pin. This is the data out. That is the data out means that is we are taking the data from the last flip flop, that is Q3. Now initially when we are making the load bar shift bar load complement as 0, that means at that time when you apply the clock pulse, the loading operation takes place. So when the first clock pulse comes, the loading action takes place. In the second pulse onwards, we are making this as 1. That means there we will get a shifting operation. So the next one is the parallel in parallel out. So as the name indicates, we are feeding the data parallelly into the flip-flop and we are taking the data parallelly. That means we are feeding all the flip-flops using the data to be loaded at the same time, that is parallelly. And we are taking the data parallelly. That means we are taking the data of each flip-flop at the same time. So here you can see that we have 4 flip-flop, 1, 2, 3 and 4, and we are feeding each flip-flop with the data to be transferred, that is D0, D1, D2 and D3, that is a 4-bit data. And we are taking the output of each flip-flop at the same time. So that is why the name parallel. So here we are feeding the data to D0, D1, D2, D3 and we are applying the clockwise and we are taking the Q0, Q1, Q2, Q3 at the same time. So that is a parallel shift register.